In the previous discussion, we explored the origins of dark energy, which drives the accelerated expansion of the universe. Among these explanations, we introduced the model that describes the universe's expansion known as the Friedmann equation. This equation is highly informative, as it not only reveals how the universe evolves over time, but also provides insights into the overall shape of our universe. First and foremost, it's important to note that today's topic does not concern the observable universe alone. The observable universe is the visible region around us when we look in all directions, much like the celestial sphere in astronomy. So, when we refer to the broader universe in this context, we are encompassing not just the observable universe but also the unobservable parts, essentially, the entire universe. In the imagination of many, even the whole universe should appear spherical. Yet, for such questions, we cannot rely solely on imagination. We require rigorous theory supported by robust observational evidence. From a theoretical standpoint, describing a dynamically evolving universe requires more than just Newtonian mechanics. We need a more powerful tool, general relativity. With general relativity, we understand that the universe's geometric shape depends solely on the ratio of the actual density to the critical density, known as the cosmological density parameter. General relativity informs us that matter and energy are essentially the same thing. Thus, the actual density mentioned refers to the density of everything we've observed, including ordinary matter, dark matter, and all known forms of energy. Critical density, on the other hand, is the minimum amount of matter needed for the universe to be in a balanced state between open and closed scenarios. If the cosmological density parameter is greater than 1, then the actual density surpasses the critical density. This results in a high-density universe where the presence of sufficient mass causes space to curve significantly. Consequently, this universe eventually curves back onto itself, forming a sphere, as described by the positive curvature in the Friedmann equation. Such a universe is termed a closed universe. However, this doesn't mean that the entire universe is spherical. We inhabit a sphere. If the universe were like this, a natural question would arise: what's beyond the sphere? How do we comprehend this sphere shape of the universe? In reality, this sphere isn't a typical three-dimensional sphere. You can envision it as a four-dimensional sphere. We exist on the surface of this sphere, which has three-dimensional geometry. I understand that visualizing a four-dimensional space is challenging for humans, so we can simplify our thinking by reducing dimensions. Imagine ourselves as two-dimensional beings living on the surface of a two-dimensional sphere. In this scenario, the entire surface of the sphere corresponds to a positively curved closed universe. For beings on this two-dimensional surface, there is no concept of an outside, because they lack three-dimensional perception. While the surface area of the sphere is finite, for beings on the surface, it's a region without a center or boundary. This is why we say the universe has no center or is finite yet boundless. Contrasting with the closed, positively curved universe is the scenario where the cosmological density parameter is less than 1. In this low-density universe, the spatial curvature is negative. The universe takes on a hyperbolic shape, resembling a saddle. Unlike the limited size of a spherical universe, this negatively curved universe, with k value less than 0, is infinitely expansive. It's referred to as an open universe. Apart from positive and negative curvature, there's an intermediate situation, a flat universe, or a critical universe, with curvature equal to 0. This corresponds to a density parameter of 1, where the actual density matches the critical density. A flat Euclidean geometry universe aligns well with our everyday experiences, much like the interior angles of a triangle summing to 180 degrees. So, apart from the overall expansion, a flat universe is essentially akin to the universe Newton envisaged. Expanding on this, if we consider topological structures, a zero-curvature plane can actually be wrapped into a cylinder. For the surface of this cylinder, it still falls under Euclidean space. As both the plane and the cylinder's top and bottom can extend infinitely, they are both part of an infinite and boundless universe. However, If we further imagine bending this cylinder so that the top and bottom connect, we get a ring-like structure resembling a torus. In this configuration, even though its surface remains Euclidean, the structure becomes a finite yet boundless universe akin to a spherical shape. While the notion of a torus-shaped universe is intriguing, current inflationary theories and observational evidence make it less likely. Plane, flat universes appear more probable. Whether it's a closed, positively curved universe, a saddle-shaped, negatively curved universe, or a flat universe, theoretically, all three shapes are possible. Moreover, these shapes hold true for each of the uniform and isotropic characteristics, as postulated by the cosmological principle. This principle states that on a large scale, the universe's matter is uniformly distributed, and the motion of this matter is roughly the same everywhere. From our vantage point on Earth, irrespective of where we look in the universe, what we see remains largely consistent. Thus, even when considering empirical observations, these three shapes are all potential possibilities for the universe. So, how can we determine which scenario describes our universe? Some have pondered whether our universe could be a finite, closed spherical space, with a light beam akin to Magellan's circumnavigation returning to our sight after encircling the universe. However, no such phenomenon resembling this, seeing the back of our heads, has been found in astronomy so far. Aside from expansion, another possibility is that our universe is truly infinite, and light follows paths without loops. This would mean that the universe isn't spherical, including the torus shape. Yet, this deduction is somewhat hasty. Are there more rigorous ways to determine the curvature of the universe? A convenient method in cosmology to ascertain spatial curvature is by observing the relationship between the number of galaxies and their distances. As per the cosmological principle, galaxies in the universe are uniformly distributed on large scales. Therefore, as we observe more distant galaxies, their numbers should increase. For a flat universe with zero curvature, this relationship should be linear. However, in a negatively curved saddle universe, the number of observed galaxies should grow rapidly with distance, as the observable region in this space is larger than in flat geometry. Similarly, in a positively curved spherical universe, due to inward bending, the observable region should be smaller than in flat geometry. Hence, the rate at which galaxy numbers increase with distance would be slower than in a flat universe. The method is simple, but what do the observations tell us? Up to now, it seems that the relationship between the number of observed galaxies and their distances indeed exhibits a linear growth. This suggests that the space we occupy is largely flat, with curvature very close to zero. This implies that, based on current observational evidence, we are inclined to believe in an infinite, boundless, and flat universe. However, a flat geometry is highly unstable for the universe. This is known as the Flatness Problem. Yet, inflationary theory has provided a reasonable explanation for this issue, as discussed in a previous article. To summarize, for today's flat universe, rather than considering it a coincidence, it's better to view it as an inevitable outcome of inflation. Hence, we can conclude that an infinite, boundless, and flat universe seems to align with our current scientific understanding.